All right, good morning, everyone. Our project here is Smart Pedestrian Counter, also known as SPEC. My name is Sarah Chesbrough.
And I'm Logan Lawrence. Here's an overview of what we will be going over today: the problem, the existing solutions to our problem, our solution, our marketing and engineering requirements, our system and software, the tests and challenges that we encountered, our budget, our schedule, and our references.
So the problem that was proposed to us was that the city of Roanoke Park wants a cost-effective, modular, non-invasive, and easily removable way to monitor the traffic on the city trails.
One of the existing solutions for these kind of problems is Citrix 3D by EcoCounter. This works by using image recognition in high traffic downtown areas to count the number of pedestrians, bicyclists, and vehicles, and it even mounts to existing surfaces. But a problem for our purposes is this product costs several thousands of dollars, which can get very costly. And the database is company provided / company managed, where our goal is to have a user managed database. Another solution is RidePod BP. This works by using two piezoelectric sensors embedded into the ground. This has a very long battery life, and it's even able to track the direction of travel. But a con to this is that sensors are installed directly into the ground, making them a permanent installation, and the control box is also low to the ground, making it vulnerable to potential vandalism.
So our proposed solution is a device that will be low cost, basically under $1,000, ensure privacy, have no permanent installations, no monthly fees for data transmission, be expandable, provide simple data visualizations, and send data to a private database.
This is the system of our proposed solution. Our whole system will consist of multiple nodes. The nodes are responsible for detecting and counting pedestrians and bicycles and sending the number counted to the internet. Data is transmitted to the internet using an intermediary between our nodes and the internet, and from there, our data will be plotted and stored on a server for the user to access and view. Here's what a node looks like. Our nodes will be powered by a solar panel. Our battery will power the whole node. We will have a motion sensor to detect motion, a camera to take pictures when motion is detected, and a transmission module to send the data, and an indicator LED to indicate that the whole system is functioning and operational.
So this is a table that compares LoRa with Wi-Fi, Bluetooth, and Zigbee. LoRa is a low-power, long-range transmission over the unlicensed ISM band. LoRa uses license-free sub-gigahertz radio frequency bands such as 868 megahertz in Europe, 915 megahertz in North America and Australia, and 923 megahertz in Asia. The table compares power consumption in watts, range in feet, and bandwidth in hertz. And this table shows that LoRa has the highest range and very low power consumption. Next slide, please. So this is the system overview of the cloud platforms that we're using. So when the LoRa gateway is online, it receives a message from LoRa node. The received message goes to the Things network, which then sends data to ThingSpeak. ThingSpeak displays the sent data in a simple graph. Next step is that the ThingSpeak graph gets sent to our project website, and then the data visualization is edited using JavaScript, HTML, and Python in order to make it more visually appealing and user-friendly. Next slide. So here are all of our marketing requirements. The three key marketing requirements that we have are 1, 2, and 4. And unfortunately, the two marketing requirements that we weren't able to do are marketing requirements 11 and 12, and that is due to the recent pandemic.
Here are our engineering requirements that correspond with our marketing requirements. Key ones would be engineering requirement 1, 2, and 3. And as you can see here, we have 2 in red. These are our engineering requirements that correspond to the 2 marketing requirements we could not achieve. And here is a list of our planned tests. These are 6 tests that we were able to complete and get done. But with our other slide of more complete tests, planned tests, we have 2 tests that were incomplete. These were our waterproofing test for creating a waterproof enclosure, putting all the components together in a single case, and our startup indication being a system diagnostic to show that all components of the system are functioning. Now our presentation will be splitting into 2 parts for our key subsystems. The motion sensor and object detection will be presented by me, Logan Lawrence, and after that, data transmission and power will be presented by Sarah Chesbrough. So for our motion sensor and object detection, we employed for object detection OpenCV, which is a library for programming, also is known as Open Computer Vision, and is used for image recognition in this project. And for our motion sensing, we used an HB100 sensor, which is a microwave sensor that employs a Doppler effect to detect motion and or measure speed. So for the Doppler effect, it sends out a wave with one frequency, and if it hits an object that is moving, it'll come back with a different frequency. And with this, we are able to determine that an object is moving. As in below, you can see the equation that we use to determine that the speed of an object, where we use the Doppler shift times the speed of light divided by our transmitted 2 times our transmitted frequency. Here's our software that we used. On the left is the software used for the motion detection and taking the pictures. First, we wait for the initial transition from 0 to 1, a rising edge, and we wait for 4 of those to occur due to the high sampling rate of our sensor and waiting for an object to come into view. Once that is achieved, we take a picture and we put it into a folder for later use, and then we wait for no rising edges for 5 seconds before we allow the system to flag a new motion to ensure that we do not detect the same person multiple times, even if we have someone walking slower too in our field of view as well. On the right, we have another program. This is for our image processing and sending data. This is running in parallel with the other software as well. Here we wait an hour, and once an hour has elapsed, we process all pictures in the folder, we save the results to a text file, and then we delete all pictures, and then we send the data using LoRa. Here's the first of our tests. This was their bulk processing time test. This was to see if with large amounts of images, whether the processing time would be linear or not, to see if it would get longer or faster over time. With this, we had many images taken of the same object, and then we put them processing with the start and end times being printed out to our terminal. With this, as you can see on the graph on the right, the line is linear. So with this, with 50 images, it took 5 minutes, and with 200 images, it took 20 minutes. Another test is for single image bike detection. Here we added increasing numbers of bikes to see at what point would OpenCV be still accurate for determining the number of bikes in a single image. On the right, we have our graph where we show the confidence rating. This is how confident OpenCV is in its result of the object that it determines something is. So when we have 1 bike in the frame, the confidence rating for that bike is around 90%. But when we have 2 bikes, the second bike added in, it's only 75% confident that that is a bike. For the third bike, though, it is below 50%. It's about 45% accurate or confident that that third bike is a bike. So for this test, we determined that when we have the number of sequential bikes in a picture, if it's below 2, we are fine with confidently determining that those are 2 bikes. But once we add in a third, that is where the program might be prone to error. Here for this test, we did a very similar setup to the previous tests, but this time we had people on the bikes. So this test was to determine the accuracy for when we have bikes and people in a single image. For this, we had an image with 1 person on 1 bike, and we increased it all the way until we had 3 people and 3 bikes. But with this, once we got to 3 people and 3 bikes, we were only able to detect 2 of the bikes, but all 3 people. But this is not much of an issue for our purposes because with the size of the trail we are looking at, we do not expect there to be more than 2 bikes in the frame of the picture. Here's our motion sensor distance test. We wanted to determine the accuracy and range that our sensor would be able to detect motion. So for this, we set up our motion sensor 8 feet high to simulate it being set up on a pole. And we made motion at 3-foot intervals from the horizontal position of the sensor, starting from 6 feet. On the right, we have a graph that shows the percentage of motions detected and the distance from the center, not the horizontal distance, but the hypotenuse if you were looking at the triangle on the image to the left. So for this, we were able to detect all motions up until about 25 feet, where we were only able to detect half the motions, but this successfully fulfills our engineering requirement where we wanted to be able to detect from 17 feet away from the sensor. Here's our speed test. We wanted to determine the time it takes to get into view of the camera to determine the number of rising edges to wait for so we don't take a picture too late or too prematurely. For this, we had a similar setup to the last test with the sensor set up 8 feet from the ground, and we walked and we ran and tried to determine the time it took for us to get in the proper view for the camera and for the sensor to detect us a number of times. For this, we determined that waiting 8.8 seconds was a comparable way to be able to capture the image of someone whether they are walking or running. But with this, while the delay time is sufficient for these purposes, if someone is moving much faster than these speeds, a different, more adaptive approach may be needed to combat this. Here's our light level test. We wanted to verify that OpenCV would be accurate in good lighting conditions. For this, we took a picture of someone in multiple different light levels. The light levels were controlled by turning on and off more light switches in a room, and the light level was taken using a lux meter. And for this, we took the average confidence rating of OpenCV as well. But for 4 being a very low lux level, with all the lights off, and 265 being a high lux level, we got the same average confidence level between all. So in conclusion, OpenCV will stay confident in its results, long as it is able to see the general shape of a human.
For the data visualization test, we need to have the data that is processed by OpenCV be sent via LoRa and allow the user to access that data. Our test was set up to have the LoRa code read a text file, then have that text file which counted the total number of pedestrians and bicyclists be sent, transmitted via LoRa to the Things network, and then TTN basically sends it to ThingSpeak for simple data plotting, and from there, the ThingSpeak graph gets sent to the website. So right now, anyone could go to our website to access the data visualizations. All they have to do is enter our URL, which is www.smartpedestriancounter.com, and then they can just go to our product section to view it. Next slide, please. The objective for this test was to prove that we could send messages from the LoRa node to the LoRa gateway. We use the Things indoor gateway, which uses a frequency of 915 megahertz. The LoRa node is the Adafruit LoRa radio bonnet, which has an attached machine-to-machine antenna, and the radio bonnet is connected to a Raspberry Pi 3. We did 4 tests, each of which had a 100% success rate. And then the distance between the LoRa node and the gateway was 15 feet. So this test showed that we could continue forward and then do a LoRa distance test. Next slide, please. So once we had determined that we could send messages from the LoRa node to the gateway, we needed to see how data transmission was affected by distance and obstacles. So we set up the gateway against a window on the 2nd floor of Salazar 2007 in the senior design room. The LoRa node was attached to the Raspberry Pi, and it was set to send messages to the gateway whenever a button that was attached to the LoRa radio bonnet was pressed. Our RX antenna basically had a peak gain of 4.07 dB. For this test, we found that when the node elevation is very low, the obstacles were severely degraded, and the line of sight is very critical for transmitting the data. Next slide, please. So given the results from the previous slide, we wanted to be able to do a test that basically had different obstacles. So for this test, the LoRa gateway was set up against a window on the 3rd floor at Allegro Apartments. The LoRa node was hooked up to a Raspberry Pi, and the Raspberry Pi was then powered by a battery pack. The LoRa node was set up to send messages when the button was pressed at various different locations. The second test was basically extended out to the 3 locations that are in that map right there. It was able to successfully transmit data as far as 0.8 kilometers or 1 mile. And the obstacle that we encountered were some trees and 1-story houses. Next slide, please. So for the expandability test, we wanted to be able to show that we could receive messages from more than 1 node. The test setup we had was 2 LoRa nodes transmitting data to the Things network at 2 separate times. We used different data points to distinguish between the 2, and we had different timestamps. So in conclusion, we were able to prove that the LoRa gateway is able to receive messages from multiple nodes. Next slide, please. For this project, we measured the power consumption for the programs and parts that are used. We used a USB multimeter, which hooked up to the Raspberry Pi, and the USB multimeter was connected to a power source. The measurements were taken after 1 more part or program was added. And as we show on the graph, for the Raspberry Pi alone, it was close to 2 watts. With the LoRa, it was above 2 watts. And then the OpenCV was really close to 5 watts. Next slide, please. So this here is the power system test. We wanted to evaluate how long the system will stay on while using image recognition and sending data consecutively. The setup is the solar panels connected to the voltage regulator, and the voltage regulator connects to the battery, and the battery gets charged by that whole system. The battery keeps the Raspberry Pi on. The LoRa node is attached to the Raspberry Pi. And then to figure out what specific solar panel that we needed, we basically used the PV solar system equation. So basically you use the value D, A, R, H, and PR. And the number that we got was 0.4856 kilowatt hour per day. And then to figure out what kilowatt per day is, you divide however many hours you're going to keep the system on. In our case, we were thinking 6 hours. And so that's basically how we got to 80 watts per day. Our ideal current range is 1.5 to 2 amps for 1 hour. So you multiply your highest range by 6 hours, and then once you figure that out, you multiply it by the voltage. And then we got 60 watts. Next slide. So here is our results for our power system test. So as you can see, the system can consistently send data once every hour. On average, it is able to continue operation for 6 hours. In some cases, it can go longer, but we just want to stick with cases where it is able to consistently do this for 6 hours. Next slide, please. So the challenges that I encountered were the original LoRa gateway, which was the Dragino LG01P. The issue was there was poor documentation. The coding that they had posted was scrambled. So I switched over to the indoor gateway because it was much easier to troubleshoot and there was better documentation. Another issue I had was Cayenne my devices. there was limitations on the data visualizations, and whenever I was able to do any data visualizations, the unit scale was incorrect. So I switched to ThinkSpeak because it was much easier to integrate it, and it had the correct unit scale.
Some of the challenges I faced were figuring out which motion sensor to use. This motion sensor kept not working with the response time we wanted. Another one was our new motion sensor had a high sampling rate, so I had to fix this with software to get it to interface properly. An early problem was we tried using TensorFlow for image recognition, but it took too long to initialize. And our GPIO library we were initially using had a hard time looking for the rising edge. So I had to switch to a different one to alleviate this issue. And here's our estimated budget, with the bulk of our costs coming from our battery and solar panel and our LoRa gateway, but the LoRa gateway is able to support multiple nodes.
So this here is our original Gantt chart that we had back in January. Next slide, please. But unfortunately, we had to make some changes due to our current situation. Down below, it shows in orange the certain things that were not complete. Next slide, please. So in conclusion, we were able to create a system that takes pictures when motion is detected. It can distinguish bicyclists and pedestrians, can send data using LoRa, and visualize that data. What we're missing is completing the node, system integration, and then testing system integration. Next slide, please.
If this project were to be completed, some future works would be transitioning to a lower power embedded system, such as the BeagleBone, which has sleep functionality, which the Raspberry Pi does not have, or switching to a very low power microcontroller able to support TensorFlow, such as the SparkFun Edge development board might be a good approach to this. Another thing would be expanding to multiple nodes and field testing those, and another would be using an analog output for a motion sensor rather than the digital one we are using for an adaptive motion sensing approach. Here are supporting courses and some skills that we have gained throughout the project: learning OpenCV, LoRa, using how to interface with Cayenne, and JavaScript programming. We would like to thank our faculty advisor, Dr. Fried Fairmond, our industry advisor, Neil Hancock, our client, Darren Jenkins, and the Office of Research and Sponsored Programs for funding, the LoRa group that meets on campus for their support, and our fellow engineering students as well. Here are our references and questions and comments.
Okay, thank you very much. Just a quick reminder to complete the evaluation form for this team as well. And now it's the time for question and answer. Please use the raise hand feature if you have questions. Anil, go ahead. Hello, Neil.
Hello.
Yes. Yes.
Hi. Great to get the presentation. And I must admit, I went to smartpedestriancounter.com straight away, and I started looking at the product view. So it was nice to be able to get that and bring up the graphs for the pedestrian counter. So that's the sort of end view of it that I got. And then I went to the code on GitHub, and it was great to be able to see some of that there and just to be able to look through it, and then the PowerPoint presentation. So looking back at the project and how you scoped it and planned it and the hardware and software, what do you think you learned?
I would say plan for multiple softwares or hardwares. So in my case, we were dead set on using a PIR sensor early on, but once we got it and started working with it, its response time was way too slow, and so we had to then put a timer on a delay on things to the point that it slowed us down to figure out what sensor do we switch to. So I'd say just have multiple plans for every thing that needs to be solved in the project.
Yeah, I agree with Logan saying have multiple plans for different parts, because you could think that something such as a motion sensor might be the easiest part, but it turns out that's like the hardest part for your project. So always have a backup plan in case something doesn't work.
So my second question on it would be, now that you've worked through it and you've been using it, would you do anything different or put any different spec in there for it being installed? A critical part of it is, how do you take it out, install it, configure it, and make sure that it all works in the field? And particularly on this, I'm asking really from experience whether or not you think one LED would be enough, or how else do you think you could have looked at this being installed in the field?
Our initial approach was to try and have it, once you have it set up and powered, to press a button or turn it on, and it would try and do something with each component in an order. And if any of that got stalled, it would blink. But you're right, we probably need a more adaptive approach, maybe even like a 7-segment display or an LCD display that would have a number code that would show what components were working and where the diagnostics stopped working. And installation, we were thinking we were going to elaborate more on that within the housing setup, but we weren't sure until later on in the project how the size of our individual components are.
Okay. So I think we may have time for one more question. Siva.
Yeah, thank you. So great presentations. Thank you. I have a question curious on this OpenCV. You mentioned that when you uploaded on an embedded platform, which is a Raspberry Pi, and now the future plan is for the BeagleBone and edge computing. So what's your experience? You think OpenCV, the memory size can handle these embedded devices? As you know, it goes in multiple of megahertz, right? So I'm just curious, what's your experience when you're uploading to these embedded systems?
Well, for the Pi, the OpenCV was actually running pretty smoothly. But for the embedded system, when I was talking about the SparkFun Edge or other microcontrollers, that would be for using TensorFlow Lite instead. But we wanted to avoid TensorFlow Lite with this iteration of the project, as it wasn't as accessible documentation-wise and not as many resources for it. And for the other system, with the BeagleBone, I have found projects online that are utilizing it, OpenCV on it. If we were looking at that because it has sleep functionality.
Oh, I see. Okay. So you can include that.
So I think we are running out of time, but I think I'll let you answer Chris's question really quick, and then we'll move on to next group. Chris?
Okay, well, they know what my question is going to be, so I'll let them answer.
Go ahead, please.
About what we learned?
Yep, same question. Thanks.
Well, I'd say definitely a lot more thorough planning, even more research than we did. We thought we did enough, and you can never do too much research. We had our first two sensors fall out on us. The second one, the response time was great, but too wide of a transmitting angle. Yeah, mostly I'd just say a lot more research. We didn't have as many coordination issues because we were a smaller group. So, but Sarah, your end?
Yeah, I think I agree with Logan on that. In terms of my section of the project, if you run into issues when it comes to using certain cloud platforms and they're just not giving you enough in terms of being able to transmit data, you're going to have to switch over to another one. And then if that one is giving you a limit in terms of like how you're going to display the data on your website, you might just have to start learning, one extra computer language that you just have no clue of how to do it. But in order for it to look clean and nice for your user, you have to do it. So I guess my advice to the upcoming seniors is that you're going to probably have to learn a lot of different languages and a lot of different tools, a lot of different hardware tools throughout the project.